Good morning and welcome to today's Siemens digital webinar entitled PCB Thermal Simulation in Simcenter 3D, Leveraging ECAD Data for PCA Thermal Simulation. My name is Carl Poplowski. I am the Engineering Services Manager for the Simcenter 3D Thermal Flow software products. And in today's webinar, you will learn how to leverage PCA ECAD data and effortlessly produce a board-level thermal simulation. We have with us today Joel Rooks, Siemens Digital Account Manager, Yannick Sigmund, Simcenter 3D PCB Exchange Product Manager, and Jean-Frederic Ruel, Simcenter 3D Applications Engineer. This is the second in a series of bi-monthly webinars we are providing to you and your coworkers. Our previous webinar covered the use of Simcenter 3D fields to provide an automated approach to using third-party boundary condition data files to define thermal boundary conditions in Simcenter 3D. Our next webinar will cover leveraging the board-level thermal representation in today's simulation in a system-level thermal simulation. I hope you enjoy the webinar today and find the information useful. I will now turn it over to Joel Rooks, who will provide a brief introduction to the Simcenter 3D's product set.
Thank you, Carl. So let's talk briefly about what is Simcenter. So I think many of you know what NX is or have heard of NX. NX is an integrated CAD/CAM CAE software suite. In 2016, with all the simulation companies that Siemens acquired, and with our vision for a comprehensive digital twin, we decided to create a simulation portfolio and we called it Simcenter. And I'll show you this in the next few slides. But NX CAE didn't go away. It's just been rebranded Simcenter 3D. So Simcenter is a portfolio of simulation products. Next slide. So this slide shows our CAE heritage. And some of the key aspects of this slide are, if you look at the top, Maya has been developing our thermal solvers and other solutions for Siemens since 1983. We acquired Nastran from MSC in 2003. And more recently, we acquired LMS in 2013, CD Adapco in 2016, Mentor Graphics in 2017. Last year, we acquired, it's not shown on this slide, Atlas 3D and Multimec for simulation and additive manufacturing tools. So Siemens has been investing heavily and as well as organically developing our many simulation tools. Next slide. So this slide gives you an overview of Simcenter. And so Simcenter has a broad portfolio of CAE simulation tools between 3D system simulation, 1D system simulation, 3D simulations, and physical testing that correlate back to our simulation tools. And all of this can be run in a Simcenter data managed environment, as well as doing a multi-physics optimization through our huge product line. Next slide. So within a single environment, you have access to a broad range of CAE tools and solvers. And today we'll be focusing on some of our thermal analysis capabilities, starting with PCB thermal analysis. All of these tools are accessible from a single user interface. So with that, I'm going to turn it over to Yannick Sigmund.
Thank you, Joel. Yannick Sigmund will now provide an introduction to NX PCB Exchange and the PCB thermal simulation capabilities within PCB Exchange and Simcenter 3D.
Thank you, Carl. So PCB Exchange is the ECAD design interface within NX or Simcenter 3D. So today we'll have a look at two different workflows when it comes to ECAD integration and simulation. So as we can see in this slide, this is showing the development cycle of a PCB design. So there are 3 stages, and in each of these stages, PCB Exchange can help you design your PCB more efficiently and more accurately. So on the left, you have the design collaboration change, where different ECAD designers can collaborate until the PCB design is completed, so at the component placement, during the routing. At the second stage, you have the design validation. So before going to manufacturing, you need to make sure that your ECAD and MCAD domains are synchronized. And we have a set of tools within PCB Exchange, whether it's validation reports or design rule checks, but we can also integrate to another Siemens tool called ELMA for visualizing those changes with markups. And the last stage is the manufacturing stage, where we can, once the PCB is panelized from the ECAD domain, re-import this information within NX and take advantage of the 3D panelization for documentation, process preparation, or jig fabrication. So in all these stages, we have robust collaboration and easy visualization of the results to understand what's going on from the other domain. So that's the first workflow. On the second workflow on the other slide, well, as we just saw from Joel, next slide please, Carl. As we just saw from Joel, once the design is completed, or even during the design cycle, once you have the ECAD information, the PCB information within NX and Simcenter 3D, this opens the door to various simulation types for the PCB. So whether it's thermal, structural, or even the system level detailed packaging review. So today we'll really concentrate on the second workflow for the thermal analysis portion. So on the next slide, if we go a little bit more into detail on the collaboration between ECAD systems, well, PCB Exchange is not just about a robust transmission of data. It's also, we need to make sure that we can support all the latest technologies that you can use today in your PCB. So rigid flex, embedded components, cavities. So we have for that multiple direct connections to major EDA tools. So we can actually, as a customer, you have access to multiple versions of PCB Exchange. So we have a generic flavor for all ECAD collaboration. And we also have two specific ones, one for Zuken and one for Mentor Expedition. So as we can see from this slide, with all the tool set and PCB Exchange, you really have the option when it comes to importing this data inside NX or Simcenter 3D to get the level of detail you're looking for. So on the left, we have a detailed packaging, all the detailed 3D models for the components, the copper with the different vias are imported as well. And on the right, you have a simplified version with an extrusion on the footprint and some filtered information. So we filtered the copper, we filtered some vias to just keep the mounting holes. So the set of tools available really allow you to import what you really need in your workflow. On the next slide, here we have a very quick comparison of all the data format or the main data format that we support. So I'm not going to review all of this in detail, but I just want to bring your attention on specific things. So if you look at the last four file formats, so IDX3, ODB++, the Zuken and Expedition file formats, these four allow you to do simulation because we understand with those file formats all the copper stack up information required for an accurate thermal simulation. But when it comes to ECAD-MCAD collaboration, if you look at the last line of this table, what an interesting feature that's very powerful is the incremental changes. And that's only currently available with the IDX3 format and our Expedition integration. So we're going to dive a little bit more into detail on what the incremental changes represent. So on the next slide, this is a quick overview of what IDX is. So basically, with IDX, you don't export the full design between the ECAD and the MCAD domain. You set a baseline between the two tools, and then after every changes is sent as a transaction, which you can preview, accept, or even reject. So this really keeps the two tools in sync when it comes to changes, understanding the changes, and making sure the two domains are synchronized. So on the next two slides, we have a quick example of how this can really help. So this is an example of a change on import, where you see that one of the connector move, so you can preview the changes as I mentioned. You can also read some comments, so you can see there's a column called comments and new comments, which is the new comment added by the NX designer or Simcenter 3D designer. So it's not just about pushing the changes and not understanding what's happening. You can really have a conversation and agree on the best placement and design for your PCB by taking into account the requirements from the other domain. So this is for importing the incremental change. If we look on the other slide, this is the same thing. So before exporting the changes to your ECAD counterpart, you can also preview the changes that you're sending. So this allows you to, for example, filter or wait before sending some changes. If some of these things are currently in progress or not finalized, you can decide to add comments and preview and send just what's required for the ECAD designer to get his or her feedback. So this is a quick overview of IDX. It's a very powerful collaboration format. And now we're going to have a quick look on the next slide at the Expedition integration. So Expedition is actually, we have a very unique and rich data features, extremely unique in the industry when it comes to the integration that we now have with this tool since the merge between Mentor and Siemens. And on top of the collaboration with changes, incremental changes that we just saw, there are lots of features that we won't get into too much detail, but just to give you a quick overview, it's not just about exchanging PCB objects, but also synchronizing libraries at this point. So we can sync on the 3D models that are used between both systems. We can also sync on the assembly around the PCB so that this representation can be used for design rule checks between the PCB and the assembly. And we also support very advanced PCB technology when it comes to RF, HDI, and embedded components. But although for those who are not Mentor users, on the next slide, we can see that we still have some tools that can be used in PCB exchange from the open architecture. So although maybe the ECAD tool you have doesn't support, for example, IDX or the Expedition integration, you can still use the compare and update capability of PCB exchange to visualize the changes and update just the changes basically that you would like to see. So you can really preview them and make a proper decision before committing on importing the change. So this works for the components, this works for the board itself, including the copper that could be in your file format if you're using ODB++ or even IDX with this interface. So this was a quick overview of the tools and capabilities when it comes to the first workflow. So now we're going to switch to the second workflow, which is the thermal analysis. So as I mentioned, once we import this data from ECAD, NX or Simcenter 3D understands the full data model of the PCB design. And basically, we leverage this to streamline the creation of the thermal model. So what we do from PCB exchange is to create a ready-to-solve thermal model. And here's what exactly we do in this case. And we'll go into more details into all of these steps. So first of all, we mesh automatically the board and the components. We assign material and physical layer stack up for the board mesh. We assign the component models for the user database, and all the boundary conditions and couplings is also created for you automatically. So we'll get into a bit more detail on this. And the two things that we'll keep in mind is that since we're in a single environment, so this is something that's very important to mention, since we're all in a single environment, whether it's Simcenter 3D or NX, we have a full CAD associativity between your CAD and CAE domain. And also you have out-of-the-box support with Teamcenter. So if you want to save, obviously, your CAD files to Teamcenter, but also your simulation, so your FEM and simulation files to Teamcenter, this is also automatically supported. So let's have a deeper look at the PCB modeling directly. So I mentioned it a little bit sooner earlier that the IDX, ODB++, Zuken, and Expedition format support all the copper information. So that means that, first of all, in terms of signal and dielectric thicknesses, if it's available in the file, we take it into account. So you have a precise stack up with the correct dimensions. For the trace itself, we understand also all the different coverage. So we can use different algorithms. So whether it's an equivalent, so basically getting a copper content average for a single layer, or taking conductivity images to have a more accurate representation of the spatially varying thermal conductivity traces. But also we understand the nets. So if you want to do a more simpler simulation, you can filter the nets. This is all understood with ODB++ and some IDX formats. When it comes to the interconnect between those layers, so again, we have understanding of the high density interconnects that exist. So if you're having true hole vias or true holes, this is supported, but also any partial holes. So micro vias, blind buried vias, everything can be supported and propagated to your thermal simulation. So once we have this copper information understood, we can create, as we see in this slide, conductivity images. And then these conductivity images are then translated for the traces to fields. Yeah, you can stay on the next slide, Carl. So the traces or the end plane conductivities are created as fields for every layer. And for every vias, we create thermal couplings between the different layers where those vias are actually. So you really get, as you can see from this slide and the PCB stack object and electronic system cooling, a very precise representation of your PCB stack for your thermal simulation. And what's interesting is that you don't necessarily need to import the copper to get this. You can also read it directly from your ECAD file format to streamline and make sure that you can run your simulation faster. So this is for the PCB. Now, if we look at the components in more detail, so the components are translated as simulation objects on Simcenter 3D Thermal. So we support multiple ways of creating those simulation objects. So we have a 2-resistor model based on the jet extender that can be used, but we also have more simpler representations. So a 1-resistor model, which is a single resistor with no junction, and also just a heat load that we call the 0-resistor model. So all these simulation objects have different model parameters. We see them a little bit here in the dialog, so we can assign to those simulation objects dissipation, different values that would be visible inside the report. And again, since we have a full understanding of the data model that we get from ECAD, the user doesn't have to generate those simulation objects manually. And what we have to streamline the generation of those simulation objects is a component catalog. So if we look on the next slide, a little bit more detail on this component catalog, well, this is a concept that exists both in PCB Exchange and Simcenter 3D. And this really allows you to create your simulation objects based on your requirements. So we see here, first of all, when it comes to the usability, you can either create your catalog from a UI, from an Excel spreadsheet, by editing directly the XML file. We have multiple ways to do this, and a bulk edit, or by entering some values manually. But what's interesting is that the mapping can really be done based on your requirements. You can have a one-to-one mapping, so every component based on the package, based on the part number, will be mapped to a simulation object with unique properties. But also, if you want to filter some passives because they don't contribute to your simulation, or if you want to, for all specific resistor, use a single model, a single representation in your simulation, this is also possible. So multiple types of mapping. So we can see here a little bit in the dialog, the part number, which is PN12 with an asterisk, takes into account all the part numbers that start with this number and will assign a specific unique simulation object. So a very powerful tool that can meet your requirements based on what kind of precision you're looking for. And finally, so what we discussed so far, if we look on the next slide, we've discussed mainly about the board level analysis. But what's again very strong with the CAD associativity that we have is that the board level thermal analysis can be reused at the system level without having to redo your simulation one more time. So the concept is called an assembly FEM. So this is similar to the concept of a CAD assembly, but on the CE side. And you can map the existing FEM to your assembly FEM, as we can see on the left. And on the right, when it comes to the simulation entities, those two can be imported. So all your different PCB board level analysis can be reused at the system level to validate the initial analysis that you've done. And again, this workflow is very powerful because since we streamline from PCB Exchange the analysis, you can run it multiple times during your design development process. So you can make sure that once you have an initial component placement with maybe an average of the copper content, you can do an initial check. Once you have the routing completed, you can rerun your analysis, make sure everything is still fine, and then finally finish with the system level. So you really shift left your simulation sooner in the design process, which speeds up your time to market and minimizes any discrepancy or respin that could, be found later in the manufacturing stage. Back to you, Carl.
Thank you, Yannick. Now we're going to have Jean-Frédéric Ruel provide us a demonstration of PCB Exchange and the PCB thermal simulation capabilities that are driven from PCB Exchange.
Thank you, Carl, for the introduction. So as Carl mentioned, I'm going to be doing the live portion of this demonstration. I'm going to be importing ECAD data coming to me in the format of ODB++ file for this demonstration. This is going to give us the board outline as well as the generic component shapes. I will then use the copper content and board stack up information to generate orthotropic conductivity fields for each layer. These will be created from the images that you see on the screen right now in blue, where the blue is copper and the red is dielectric. We will also be customizing PCB component catalog, where we will look at the thermal properties for each of the electrical components based on their package name or part number. We will then combine these informations for both the component and the board to automatically generate a model through PCB Exchange. PCB Exchange will mesh the board and the components, as well as apply the material properties and the boundary conditions specified in our board thermal conductivity file and in our component thermal catalog. We will then be able to run the analysis, get temperature results for all the layers of the board, as well as for every component. We will then get an updated ODB++ file from our ECAD friend or colleague. We will compare this new ODB++ file with the actual PCB design that we have currently, and we will update this design and re-solve our analysis. So that's the plan for our presentation today. Let me switch over and make myself presenter. There we go. So we start off this workflow by opening an empty part file in Simcenter or NX. We will switch over to PCB Exchange. And our first order of operation is to import the ECAD data. As I mentioned earlier, I will be using an ODB++ file for this demonstration. Simply browsing to that ODB. And I'll go ahead and import. So what we get is our board geometry as well as our components, simplified representation. If I go to our PC Design Navigator, we also see that we get for each component, we get the reference, their reference designator, their package name, and part number. This information will come in handy when we use our component thermal database to assign thermal properties to each of these components. We will be referencing either their package name or part number, and that's how the association between the ECAD data and the thermal data is going to happen. But first off, we will want to look at the board thermal conductivity. So we will be once again pointing to our ODB++ file. And in this file, we have all the stack up information for the board. First off, we have information on all the different nets in the board. And if we wanted to, we could filter out certain of these nets and only have a simplified representation. For this model, I'm going to keep all the nets. We also get the vias and other plated holes summary of the file in this dialog right here. So for this design, we have two types of vias and one type of mounting hole. Here we control how we are going to model their plating, their copper plating. So we can have them filled or not. And we can also modify how much of a plating they have. So by default, they have a 1 ounce of copper, but this is a value that you can change. For today, I do know that the smaller vias, so the 0.25 diameter vias, I want to take into account or to account for them being completely filled with copper, but we'll keep the larger vias with a simple plating thickness of 1 ounce of copper. So once that's done, all we have to do is have PCB Exchange calculate the thermal conductivity for each layer. What it's doing is creating the following images. So in blue here, we have the copper, in red, the dielectric. And what PCB Exchange did with these images is it discretized it into these small squares. So each square is a calculation point that will get an equivalent Kx, Ky, and Kz conductivity value, so orthotropic properties. And this will create a X, Y spatially varying field for each layer. So for each signal layer, we have a separate image. So here's a ground plane, different signal. And at the end here, we also have the vias. So you can see that the larger vias, in green, we have the copper, the red dielectric. So for the smaller vias, they are fully filled with copper. For the bigger vias, we have a small a copper 1 ounce of copper plating from our settings earlier. And so between each signal layer, wherever they're placed, we have these via images. So we can, through this way, we can have, we can model vias that are blind or buried, for example, as well. So now that we have the board thermal conductivity calculated, our next step is going to be to look at the component thermal database. For this design, I have one specially, I have a component catalog specially made for this demonstration. The component catalog that comes with PCB Exchange is just an example file with some example values. It isn't intended to be used out of the box since those values are made up values. It is simply an example of how to set up this catalog. This catalog can be modified either directly in this user interface here, like this, for example, or it can also be edited directly in Excel, which oftentimes is a lot easier. As Yannick mentioned, this component thermal database is the matching between the electrical component in the ECAD system and this thermal, and these thermal properties are all based on either the package name, part number, or reference designator, even if it's for a specific board design. In our case here, we have the package being our reference. And in this thermal catalog, we can, this is where we store the resistor model for the different packages. They're the different resistance values for junction to case, junction to board, case to board. We also have a nominal heat load that is mostly a reference heat load. These will get updated in the simulation based on what the operation is for the board. And we also have some reference temperatures for max case temperature or max junction, max case or max junction temperatures, which are used for reporting purposes. Let me just undo the change I did before, put that back to 110, and update our catalog. So we have our board thermal conductivity being accounted for here, as well as our component thermal database. We have everything we need to automatically generate our PCB thermal model. So I'm going to click OK. And what PCB Exchange is doing right now is meshing the board, meshing the components, applying the board thermal conductivity properties to the board. To do so, it is creating a PCB stack physical property. And in this PCB stack, we will have properties for each layer referencing fields, orthotropic conductivity fields that are coming from our board thermal calculation that we did just prior to this. We will also get simulation objects for each PCB component on the board, as well as an overall convection to environment constraints, which we can modify and remove. So let's first look at how the board was modeled. If I go to the board here, I'll see that I have a PCB stack. In this PCB stack, I will see my 11 layers for this board with signal layers and dielectric layers being modeled. And each of the signal layers reference a trace coverage field that are right here. And as we saw in the webinar of the last webinar, we can actually preview these fields graphically in the UI directly. So for layer 1, let me hide the geometry, we can see that the copper content looks something like this, similar to the image we saw earlier. For layer 3, which is a ground plane, it is mostly copper, so entirely filled in. So that is for how the board is modeled. Let us look at the PCB components. So each PCB component on the board, it has a simulation object associated to it, a PCB component simulation object. This is where the PCB component catalog filled in these values. So for IC1 here, I have a 1 resistor with a 20 watts, a C per watt thermal resistance, a maximum case temperature, and a default thermal dissipation. These are all coming from the catalog. Obviously, the thermal dissipation is probably not right, since this is a nominal dissipation coming from just a reference. Thus, based on the actual operation of this board, I know I need to update these values. So I can come to this expression menu in Simcenter, and I can modify these dissipation values. I can do so in Excel or directly modify the values here, which is very quick in this case. Once I've updated my values, next I want to look at my boundary condition. So like I mentioned before, PCB Exchange creates a default convection environment on the entire board and components. In my case, I want to run something that's actually in vacuum, so there's no air. So we will remove that boundary condition, and we will replace it with a radiation to environment boundary condition. We will apply it to all the board and all the components, assuming there's a substrate or a film over the entire board that gives it all the same emissivity. We'll apply an effective emissivity of 0.9, and we'll radiate it to a specified temperature of, let's say, 40 Celsius. Now, I also know that this card is mounted to something, so we'll represent that with a temperature constraint on the edge here. And once again, that temperature will be 40 C. We now have our boundary conditions and our simulation object set up. I'm simply going to make one little change in the solver parameters to make this model run a little bit faster. And we'll go ahead and solve. We're actually going to solve this live, since the model takes about a minute to run on my computer here. What the solver is doing, and what you probably noticed, is that for the board mesh, it's actually in Simcenter, it is only a single 2D shell, or not a single shell, but a single 2D mesh cell on top of the board. And in order to get temperatures for each layer of the board, what we're using is multi-layer shells. So the PCB stack that we were looking at is a special instance of another concept in Simcenter 3D thermal, and that is the non-uniform multi-layer shell. And what that does is that at the solve, the solver is creating 2D shells for each layer. So each layer will get its own in-plane conductance, and we'll couple each of these shells that represents the layers with the appropriate thermal conductivity based on the layer thickness and the trace coverage orthotropic properties that we applied. And so in post-processing, we'll still see that one shell layer of shells, but we'll be able to post-process each temperature, each layer of the temperature of each layer individually. So my run is done. And let's look at the results here. So here are the temperatures, a little bit hot. And if I hide everything and just show the board, we can see here under temperature that I have temperatures for each ply or each layer in the PCB. So I can get individual temperatures for each layer and really see the gradient through the board. You'll notice that we have one component that's pretty hot, 121 degrees Celsius. We can probe the temperature directly from post-processing in this contour plot, but we can also, PCB Exchange also generates a report. So let me simply browse to where we solve. We have here a group report that in HTML format that gets populated, and it will highlight in red any components or junctions of components that get hotter than our max temperature that we specified in our component thermal database. So we can see that there's 3 components here that are too hot. And I know for a fact, having run this before, that these components are the 6 components here. And so if I wanted to improve these results, I know that in the final design, these are actually coupled to a heatsink. So I can model this at the board level without necessarily yet going to the assembly level analysis. We could model this with a convection to environment, for example. So an added heat transfer to our environment with a fixed heat transfer coefficient, let's say 30 watts per meter squared, once again to our 40 degrees sink temperature. And that's all we would need to do. We could rerun this and see the impact on the result. But while I was working on this, while this was solving, my colleague actually sent me an updated ODB++ file. And since we're using ODB++, I'm going to compare and update with the new ODB and see the changes. If I was working with IDX and the incremental workflow that it allows, I could also import an incremental file at this point and really just get the changes. But for ODB, we will be using the compare and update. So my ECAD colleague has sent me a new ODB++. We're going to browse to it. And what this is going to do is it's going to compare the new ODB with what's in the NX model right now. And it's found that the board geometry hasn't changed, but there is one component, this IC1 component, that has moved. And we can preview the change and see, and see where it's moved and actually apply it. So I've actually updated the board here already. And at this point, we could go ahead. Let me do a quick save. At this point, we could go ahead and update our FEM and SIM file. We can simply do that through the ESC solution dialog here, update existing, and we can update 2 things separately, either our components because they moved, or our PCB since this component moved, the trace and copper content probably also changed on this board, and so we can update just the PCB stack up as well. So we could go ahead and recalculate our board thermal conductivity and update that separately from the components. For now, let's update the components. I'll just browse to the to our sim file that we created. And still using the same component thermal database, we can update the components. So if we make a change to this component thermal database, we could also update all the boundary conditions that way, instead of going in and manually changing the values. So now that, as you saw, the component location updated and the boundary condition got, for the PCB component, also got updated, and then we'd be ready to solve at this point and see the impact of that move on the component. So this is what I wanted to present today. If Carl, if you want to make yourself presenter again, I do have just a summary slide of what we saw. We started off with an ODB++ file. We could have used an IDX file as well, or any of the other formats that we support, to import the board geometry as well as the simplified representation for each of the components. In the ODB++ file, we also had our board thermal conductivity. We had all the information for the PCB stackup as well as copper content. So we used that to calculate the board thermal conductivity file for each layer, as well as the impact of the vias between the different signal layers. We edited and looked at the PCB component catalog, how we could edit it, and how it was used by PCB Exchange to generate thermal data in our PCB component simulation object. We then got PCB Exchange to automatically mesh the board and the components, applied the boundary conditions and the material properties for all the different components and board. We then ran the solution and got temperatures for each layer of the PCB stack. Our colleague then sent us over a new ODB++ file that we compared to our existing NX model. We saw the moved component, and so we updated the FEM and SIM thermal model of the PCB board, and we're able to move along and complete iterations on this design. So that's all I wanted to present. I'll let Carl wrap this up.
Thank you, Jean-Frederic. Pretty impressive demonstration. Particularly, I think what we need to really focus on is that you can run these thermal simulations at the board level very early in the design process. And as the copper content changes in the board due to either electrical issues or to address thermal issues, you can respond very quickly with new temperatures. So let's kind of wrap up what we've seen today. We talked about Simcenter 3D, the very long and successful CAE heritage in the industry, starting back in the late 70s with the Ideas TMG software. And of course, now access to many powerful CAE solutions with Simcenter 3D, and using one system and one user interface, instead of having multiple software solutions with different data files, user interfaces, and things like that. We moved into PCB Exchange. We talked about the different ECAD formats, including Altium, ODB++, IDX, and also the Mentor graphics capabilities. We imported and talked about importing and exporting ECAD and EBCAD incremental changes. We looked at creating a ready-to-solve PCA, printed circuit assembly thermal model, and we covered user or project-specific component libraries, and looked at the explicit but efficient representation of board copper and vias, in that you only have one set of shell elements, but at runtime, the software creates the multi-layer shells with calculation points on each layer. And then we touched on easy reuse of the PCA thermal representation at the system level. And of course, that will actually be the subject of our next webinar in a couple of months. So the next webinar, keep your eye open for the invitation. We'll look at leveraging the PCB exchange thermal model of the PCA in system level simulations, actually 2 of them, an Earth-based one and a planet orbit-based simulation. And also, I just wanted to mention that if you'd like to look at our last webinar, I'll give you just a minute to jot down the YouTube link to the last webinar where we talked about using Simcenter 3D fields for leveraging third-party thermal boundary conditions within Simcenter 3D. Let's move on to questions and answers. First of all, I'd just like to point out that if you desire more information on these software tools, you can contact Joel Rooks at Siemens or myself, Carl Poplawski, and you'll have plenty of time to jot down these email addresses while we're addressing questions. So I'll give everybody a minute to perhaps formulate some questions, and if you could just type your questions in the chat, I'll read those questions and then direct one of our panel members today to answer those questions. So I'll give you just a moment. Well, it looks like I have actually a couple of questions from the same audience member concerning component catalogs. The first question is, can you have dedicated component catalogs for different engineering projects? JF, would you like to handle that?
Yeah, sure. Yeah, so there's nothing stopping you from having multiple catalogs. Essentially, the catalog is saved on disk as an XML file that gets read by PCB Exchange and ESC. And so that XML file, you could have more than one, and you could share them on a shared drive or manage them in Teamcenter. And PCB Exchange essentially points to this catalog through an environment variable. So you can have that environment variable to point to a specific location depending on the project you're running on.
Okay, very good. And the second related question is, can I modify the component characteristics locally without changing information in the component catalog?
So yes, a little bit like I did for the heat loads, you can do the same for all the other values. You can manually change them or actually manually enter them. Also, you still have access to the catalog in Simcenter. So I didn't show that in the demo, but if you create a brand new PCB component, you can actually go and pick a component from the catalog, and Simcenter will fill out the form or the simulation object for you based on what's in the catalog as well.
Thank you, Jean-Frederic. Are there any additional questions? We'll give the audience another minute or so. All right, well, we'd like to thank everybody for their participation today in the webinar. And again, keep your eyes open for an invitation for the next webinar in a couple of months. We do these things every 2 months. Thank you very much, and this concludes today's session.